So, firstly, I would like to start the presentation with this kind of spatial intelligence questions. For example, if we ask the model to identify like which one is longer, actually it's a very simple question for human. Like as human, which one do you think is longer? So basically, as human, we can quickly identify like A is longer. But when we try with the GPT-4V model like 2 years ago, or we can see like GPT-4V tell us both of them are of the same length. And then if we try it, sorry, I want to start my camera. Oh, yeah. And then if we try it with the current latest model, we actually see like the current model still identify them as the same length. I think this is actually okay 2 years ago when we first have these foundation models, but actually it's already 2 years later and we have a lot of new capabilities developed. So it's actually very concerning, like the current model are still performing such bad on this kind of questions. Then the reason is that for this image, the style is very similar to visual illusion. So we basically try to see whether the model can really understand the concept, like we can change the two lines to two pencils. And this time, the model can understand the concept. And we can also change them to two real-world objects, and the model can do it correctly. So basically, the model is not really understanding the concept when we change the image styles. So they are basically just trying to memorize this image style. And if they see this in the training data, they will just recognize this. For example, whenever they see this image style of this kind of two lines, they will link them to the visual illusion example and they will just do not see the image anymore, just answer the question. So this makes us very concerning about how we can really make the model to understand the geometric centric concepts. For example, there are a lot of testing set about whether the model can understand the shape color and whether the model can understand the orientation or pose. And another thing is if there are two objects, we want the model to understand their spatial relationship. For example, when we have this kind of different orientation or pose from human, we just try to ask the model to also have this egocentric view. And then we also recognize like for the simple spatial relationship, the model always try to predict the cup is on top of the table whenever they see a cup and a table. Even if the cup is under the table or on the left side of the table, on the right side of the table, they will just stick to the answer like the cup is on top of the table. This is definitely not what we want the model to do, that they are simply biased towards to the prior they see, especially in the language side. And then we also see like the model cannot do well for the spatial relationship. Even for this very simple question, sometimes the model can make errors. And also like the spatial relationship, if we ground them to some map, the map setting is also more complicated for the model. So essentially, what we care about here is like the model is not very good at the geometric structures. As a result, we want the model to not only learn about this kind of geometric structures, but also was able to track the geometric structure changes over time. So we want to include the ability to understand dynamics. This kind of dynamics related to state changes, related to the navigation, related to the word modeling or spatial reasoning, and also construct the episodic memory over the entire like long sequence like a video. So here, essentially, we have this kind of major problem we really care about, that the current large language models, if we try to add the multimodal ability, they are not very good at the geometric information understanding. And then we try to see why. So if we trace back to how human is learning this kind of geometric knowledge, we basically try to interact with the physical world. For example, we just learn within the environment, we can navigate, we can traverse, and we basically know more about how these different parts are connected, and we just locate ourselves in this geometric layout. So that is how we learn about this geometric knowledge. But for machines at the current stage, we are not able to afford this multisensory interaction data. They're super costly. So instead, we don't really learn from dynamic data from interaction. We learn from the static data, especially we collect maybe all the videos from the world and trying to make the model learn about the spatial dynamics based on these static videos. For example, if the book is falling down, we can see like the spatial relationship between the book and the table is changing. So the book is originally on top, like higher than the table, and then gradually it kind of start to be on top of the table. So that is what we are learning at the current stage. And for the model architecture wise, what we are doing is we just sequence everything. So make everything as a sequence. For example, if we have the image, the natural way we are doing is just make the image as a sequence of the patches. And if we have the video, we just make it as a longer sequence of the patches. And for the chart, it's essentially the geometric feature based layout, but we just simply pass all the layout into a sequence of the patches. And even for molecular, they're essentially just the graph structure, just we just kind of simply treat them as a sequence of tokens. So all of this basically tell us one thing, that when we're trying to learn about the geometric structure, if we just directly connect the visual perception to the language tokens, it's just ignore all the geometric layouts. So what we are doing here is maybe we're thinking we should help the model to better think from this like spatial layout perspective and help the model to do better abstraction about how the space is structured. For example, as human, we actually can build this kind of internal belief, like even if we don't really see the environment, if we just see the natural language description, like place a blue chair behind a red chair, put a yellow chair behind the blue chair, then put a book on top of the chair that is in front of the blue chair. What we can see here is like the model basically, as human, we basically can try to imagine the space, like we put the chair gradually and make them essentially the geometric layout as described in the language. So this is the internal belief in our human brain. And then we also can do this mental simulation over this internal belief. For example, we will be able to answer what if questions, like we have the layout and then we can say like, what if I turn right, what will be behind me? So what we are trying to do here is for that intermediate layer, trying to do the reasoning, we try to abstract it into some spatial belief. And at the current stage, what we tried is what kind of representation is the best for this spatial belief. So we try to work on this. So we try to work on this kind of question that whether we could ask the model to reason from the limited views, especially if there's are unseen objects, whether the model can infer their relationship. Basically, if we have these four different views, as human, we try to connect the dots. And then if we only see the viewpoint four, we can try to answer the question, like what is to the left of the black bag. So if you just see this single image from viewpoint 4, we can never answer the question here because the left side of the black bag is actually outside of this scene. So we cannot answer the question for this unobservable part. But as a human, as we mentioned, we can try to connect the dots. We will try to build up this spatial mental model. For example, we have the first viewpoint and we learn that there's a door in front of the bag. And then we can try to switch to viewpoint 2. We switch to viewpoint 2 because we can check the orientation and the pose of this bag, and then we can know this is actually the second viewpoint, and there's a desk on the left side of the bag. And then we switch to viewpoint 3, and we can also, based on the pose of the bag, we can understand there's a window behind the bag. And after that, from the viewpoint 4, we can also from the pose and then connect the dots, realize like there's a sofa on the left side of the bag. So as a result, as human, what we try to do here is we try to ask the model to try to imagine the space layout. And then like when we answer the question from viewpoint 4, we can do mental rotation. So we know like from viewpoint 4, now on the left side of the bag, there's a window. What we can learn from this example is that we want the model to connect the dots. Even if they don't really see the object from the current view, we want the model to reason from other views. So this is reasoning or thinking from limited views. And then to create this kind of views, we try to have different movement patterns. Like we have the rotation movement pattern, and we ask the model to like working around the objects or working among the objects. And then when we try to create the questions, we have a fine-grained question taxonomy. We can ask like what if dynamics, we ask like what if the agent is working this way, or what if the agent is rotating, and what will be the state changes here. And then we can also ask the model to learn about spatial relationship based on different reference. Like we can ask like where is the object to the agent, or where the agent changes if they switch to the current view. And we can also ask the model to answer questions like where is the object of the washing machine to the sofa. And then we can have this kind of different perspective taking questions. Like if I say from the current view, then basically we imagine there's an agent stay in the current point. And then we can ask questions related to like from the viewpoint of sofa, where is the kettle, where is the washing machine? And we have different visual patterns involved in the input. So essentially, we're just trying to see what kind of questions is very difficult for the current foundation models. As a result, this is how we can build up our data set. We have different movement patterns and we have different question types. And then this actually contribute to a very large data set containing around like 10,000 questions. And then when we test on this large data set, we realize like even for the current foundation model, the most state-of-the-art model, their performance is still much lower than the human performance. So their performance is just very close to 50%. As a result, the next thing we try to do is we try to teach the vision language foundation models to approximate the spatial mental models. The first thing we try to approximate is just if we want the model to reason from different viewpoint changes, and there are a lot of unseen objects, the first thought we have is just inject this like unobservable object into the model. For example, if I just change from viewpoint 1 to viewpoint 2, I can just interpolate all the view change images into the middle. And then we actually unfortunately didn't see much of the improvement. So it basically means like for the current foundation model, the vision input is not really the helper, but they are mostly the noise. And then we are thinking, we just ask the model to reason more in the language side. So for example, we can ask the model to reason step by step. It's kind of like the chain of thought based reasoning chain. And this kind of prompting actually will make model to improve around like 3-point absolute score. But then we are thinking as human, the most intuitive representation is try to ground everything into a map. As we just mentioned, we have this layout constructed in our mind. So what we are doing here is maybe we don't just use free-form natural language. We can use some structures like the coordinate map. We can ask the model to describe where is the location of each object and what are their relationships. So here, the performance actually improves further to maybe 4%. If we review what we just talked about, we have this kind of different ways to ask the model to approximate the spatial mental model. So they are kind of like the scaffolding for the model's thinking process. They are just different kind of chain of thought. And for the first one, the chain of thought in the visual space, actually it's not improving much. And for the chain of thought in the language space, we actually identify like structured output, like the cognitive map will be much more helpful. As a result, we are thinking like this is just the structure trying to help in the prompting stage, but maybe we can also make this kind of structure to be helpful in the training stage. So the next thing we are trying to do is we try to do supervised fine tuning, and we try to compare about the different kind of training data. Like we can annotate the training data, just try to provide the QA pairs, and we can also ask the model to do free form reasoning. And then another thing is we just ask the model to construct the cognitive map explicitly, and then we can reason on top of that. So if we compare these three different kind of training data, it's very like interesting that if we just construct the map, actually the performance will improve much more compared to just do the plain reasoning or just do the raw QA. So the performance is improving around like 7 to 8% absolute gain. So I think that's pretty huge. And then if we just do supervise the training, it's just we try to see we can improve the model to provide a better way to construct the spatial belief. But then we are thinking like, this kind of spatial belief in our setting is cognitive map. And then whether this cognitive map can be really reflected in the training process, like whether it's really because of this cognitive map that the model's QA result is better. So what we are trying to do here is we try to trace back to the model's training process, learning process. For example, if we do not do any training, we just ask the model to output the cognitive map. And then in this case, we can see the model is seemingly able to output the map. But if we took a close look, actually all the maps, they're just trying to memorize the format, memorize the style. But if you check all the numbers, they are totally wrong. So it basically means the model is just able to try to output the cognitive map format, but they are not really able to locate the objects and figure out their spatial relationship. But after the training, we can see like when the model's QA performance is improving, their cognitive map ground, if we calculate the similarity between the cognitive map and the ground truth cognitive map, their similarity is actually improving a lot. As a result, basically better QA is actually improving the model's ability to construct better cognitive maps. So as a result, we actually figure out this intermediate layer to connect the spatial reasoning and the language model reasoning is basically construct this cognitive map. And we are thinking if we really want the model to learn about this spatial relationship from the feedback, maybe we can also try the reinforcement learning algorithm. But at the beginning, when we try the reinforcement learning algorithm, for example, the first bar is the like frozen VLM, and the second bar is reinforcement learning, and the third bar is the self-supervised fine-tuning. And we can see like the reinforcement learning bar and the self-supervised fine-tuning bar basically show that the reinforcement learning is not really working well. So their performance actually the supervised fine-tuning can improve around 10% absolute score compared to the reinforcement learning. As a result, we are trying to ask the model to emerge this kind of spatial cognitive map ability. It's very similar to what DeepSeek R1 is doing. Like for DeepSeek R1, what they are doing is they try to ask the model to firstly learn about or from this cold start stage about how to do the general reasoning, and then they use the reinforcement learning to further force the model to emerge this intelligence about how to better do the reasoning. So here we are doing the same. Like we ask the model to firstly do the supervised fine-tuning on the map data, and then we ask the model to see whether they could emerge the reasoning over these maps. And then the model can improve a lot. So basically, we can see this map then reason paradigm is working pretty better compared to just the raw RL or compared to the raw supervised fine tuning. Basically, in this work, what we try to do is we want the model to develop this kind of spatial internal belief, and we hope the model to learn about how they can connect the dots, especially like think from limited views. Yeah, so if there's any like questions, you can feel free to ask. And we basically want to ask this kind of fundamental question, whether these foundation models can learn better spatial priors from this kind of vision model, and also whether we could make the model really improve for the spatial intelligence. So we have a lot of related work. For example, this work we are talking about is essentially just trying to think from limited views, but we also try to like ask the model to really look inside their like internal working mechanism to open up the model and see why the spatial reasoning is very hard. And we can also try to locate the model parameters by kind of do the model merging. And then we also have related work related to layout VLMs and how we can learn better geometric features for the like vector graphics. And we also collect all the work together into this awesome spatial intelligence paper GitHub repo. So if you are interested in this direction, we are very excited to talk more. Thank you.